Ever catch yourself just staring at a clock?
Uh,
Or maybe like counting down the minutes until your coffee's ready,
Mm.
and you kind of stop and think, what are numbers really?
yeah,
We use them every single day,
yeah,
but we rarely stop and consider like the intricate world that they hold within.
yeah. It's easy to take numbers for granted,
Quarterly.
just to kind of see them as tools for
Okay.
calculation and
Right.
quantification. But there's so much more than that. They're the fundamental building blocks of mathematics,
Mm.
with all these hidden depths and surprising connections that are just waiting to be uncovered.
And that is what this deep dive is all about. We are taking you on a journey through excerpts from the book What is Mathematics by Richard Courant and Herbert Robbins.
Great book.
And don't worry, you don't need a PhD in mathematics to enjoy this one. The book breaks down these complex concepts into these surprisingly digestible pieces.
Yeah, it's a testament to the book's relevance.
Mhm.
It was originally published in 1941,
Wow.
and it's been updated over time to reflect new discoveries and new advancements.
So they've been adding to it.
Yeah, they've been adding to it. The
Yeah.
mathematician Ian Stewart added a whole new chapter,
Oh, cool.
highlighting advancements in the field.
Oh, very cool. I
Yeah.
like that they did that.
Yeah.
Okay, so let's begin our mathematical adventure. Where better to start than with the basics?
Mhm.
Natural numbers,
Yeah.
those counting numbers we all learned as kids, 1,
Mhm.
2, 3, and so on.
Mhm.
What I found really fascinating is how the book visualizes these numbers,
Yeah,
making the abstract concrete.
absolutely.
Yeah,
They use this very simple but powerful system of dots arranged in boxes.
go.
And it's remarkable how this simple visual representation brings basic arithmetic operations to life. Addition, multiplication, subtraction.
Yeah, it's like you're seeing these equations come alive right before your eyes.
Exactly.
It's not just these abstract symbols anymore, but you're actually seeing 2 dots plus 3 dots equals 5 dots.
Yeah.
It's making those fundamental laws of arithmetic so much more intuitive and relatable, I think.
For sure. And it really helps bridge the gap for people who might feel intimidated by math
Right.
or intimidated by abstract mathematical symbols.
Yeah.
The book takes this visual thinking a step further
Okay.
by exploring different number systems.
Which is where I think things start to get really interesting.
Yeah.
So we typically operate in base 10, using those 10 digits from 0 to 9.
Mm-hmm.
But the book throws a curveball with base 7.
Base 7 is just the tip of the iceberg.
Okay.
Historically, different civilizations have used different number systems.
Really?
Yeah. The Babylonians used a base 60 system.
Wow.
The Mayans used base 20.
Yeah.
And even today, we see remnants of these systems in our measurements of time and angles.
Wait, so our way of telling time has roots in ancient Babylonian mathematics.
It does.
That's incredible.
Yeah,
But why these different systems? Was it just for the sake of being different?
not at all. The different number systems offered practical advantages for
Yeah.
specific purposes.
Okay.
The Babylonian base 60 system, while it seems very complex, actually made calculations involving fractions and astronomy remarkably elegant and easy. And base 12 had its own benefits because it's divisible by 2, 3, 4, and 6.
Interesting. So it's not about one system being superior, it's about different systems having unique strengths,
Exactly.
depending on the context.
Mm-hmm.
The book gives this example of how our familiar number 109 in base 10 translates to 214 in base 7.
Right.
Now, I'm no mathematician, so this initially seemed like a foreign language to me.
It's a shift in perspective, but it highlights this ingenious invention of positional notation,
Okay.
which we can thank the ancient Sumerians for.
Positional notation.
Okay.
All right, for those of us who maybe didn't major in mathematics, can we break that down a bit?
Yeah, so essentially it means that the position of a digit in a number determines its value.
Okay.
So in the number 109,
Yeah.
the 1 represents 100 because it's in the hundreds place. Right. But in the number 214 in base 7, the 2 represents 2 groups of 49
Okay.
because each place value is a power of 7, not 10.
So it's like a completely different way of like organizing and understanding numerical values based on the chosen base.
Exactly.
Mind-blowing. And to think we have the Sumerians to thank for this elegant system.
Yeah, their invention revolutionized mathematics.
Wow.
It paved the way for more complex calculations and abstract thinking about numbers. Imagine trying to do advanced calculus with Roman numerals.
Oh my gosh, that would be
Can't even
a
imagine.
nightmare.
Yeah, that would be a nightmare.
Yeah.
Speaking of pushing the boundaries of numerical thinking, the book then takes us on this exhilarating journey into the realm of the infinite.
Yes. It's a realm where our intuition about numbers can be both enlightening and a little bit misleading. Yeah, and the book really doesn't shy away from this topic at all. They introduce this powerful tool called mathematical induction to help us navigate this seemingly paradoxical concept.
Yeah.
Now, before you picture us huddled over equations with calculators in hand, it's not as daunting as it sounds.
Not at all. Mathematical induction is more about like elegant logic than just brute force calculation.
Okay.
It allows us to prove statements about an infinite number of numbers without having to test each one individually.
Right, because you can't count to infinity.
Right, exactly. You can't just keep going and going.
Yeah.
But with induction, we can reason our way to these truths about infinite sets.
Okay, so how does this mathematical induction thing work?
Right.
The book uses the analogy of a domino effect, which I found incredibly helpful.
It's a perfect analogy. So you can imagine this endless line of dominoes that are perfectly arranged. If you know for certain that knocking over the first domino will cause the second one to fall, and that this will continue down the line indefinitely, you can conclude that all of the dominoes will eventually fall even if you can't physically see it happen.
Right. Okay.
It just makes sense.
So we're applying this domino effect to the world of numbers.
Exactly.
Okay.
The book gives an example of the sum of the first n integers. Let's say you want to prove that the formula sub n n1 holds true for any positive integer.
Okay.
This seems daunting, but induction makes it a lot easier.
All right, walk me through it.
Okay.
Let's pretend I'm seeing this formula for the very first time.
Sure. So first we test the formula with the smallest possible value for n,
Okay.
which is 1. In this case, sub would simply be 1.
Okay.
Plugging 1 into the formula, we get 1/1/1/2, which also equals 1.
Right.
So our first domino falls.
Okay.
So then we assume that the formula is true for some arbitrary integer k.
Okay.
So we assume that sub k, k1 here is true. This is like saying if the domino in our line falls...
This can hit the next one.
Exactly.
Yeah.
The final step is to prove that if the formula is true for k, it must also be true for k1. In other words, we need to show that sub k1 sub k1 k2 half.
Okay.
And we can do this by building on our assumptions about sub k sub.
So each domino, each number in the sequence relies on the previous one to create this chain reaction of truth.
Precisely.
It's very cool.
Yeah, and by proving this relationship between consecutive numbers, we've proven that the formula holds true for an infinite number of cases.
Oh, wow.
We've tipped that first domino and set off a chain reaction that goes on to infinity.
It's very cool.
Yes.
But it still kind of begs the question, what is infinity?
Right.
Is it just a concept, or is there something more to it?
That's the question that has puzzled mathematicians and philosophers for centuries.
For sure.
The book kind of delves into this inherent mystery and paradoxical nature of infinity.
Yeah.
And how there are actually different sizes of infinity.
Different sizes.
Hmm.
Okay, now my brain is really starting to hurt. Isn't infinity, by definition, just endless?
It seems very counterintuitive.
Yeah.
But let me explain. So while the set of all rational numbers, fractions like a half, 3/4, and so on, is infinite, it's also what mathematicians call countable or denumerable.
Wait, hold on. Countable. How can you count something that's infinite?
You're not counting in the sense that you're listing out every number, because that would be impossible.
Of course.
You're showing that you could arrange them in order sequence where every rational number eventually gets a number assigned to it.
Okay, so even though it's infinite, there's a way to systematically count them.
Exactly. Now contrast that with the set of all real numbers, which includes those rational numbers plus irrational numbers like pi and the square root of 2.
Okay.
This set is considered uncountable.
Uncountable, meaning?
Meaning no matter how hard you try to arrange them in a sequence, you'll always miss some.
Wow.
There's just no way to create that one-to-one correspondence between the natural numbers and the real numbers. The book uses Cantor's diagonal argument to illustrate this.
Okay, I've heard of Cantor's diagonal argument, but to be honest, it's always seemed a little beyond my grasp. Can you break it down for us?
Yeah, so imagine if you tried to list out every single real number as an infinite decimal.
Okay.
Cantor's argument shows that you could always construct a new real number that's not on your list.
Oh.
How would you do that?
Yeah.
By creating a decimal that differs from the first digit of your first number, the second digit of your second number, and so on.
So you're creating a number that's dodging all of the other numbers.
Exactly.
To create a new one.
It's a very clever argument, and it really drives home that the set of real numbers is a bigger infinity than the set of rational numbers.
Wow, so we've got countable rational numbers and then this bigger infinity of real numbers. Are there any other special categories within the real numbers?
Yeah, so then the book introduces the concept of algebraic numbers.
Okay.
These are numbers that can be solutions to polynomial equations.
Okay.
Think of the equation x squared minus 2 equals 0, where the square root of 2 is an algebraic number.
Okay, very cool.
Mm.
And are those algebraic numbers also uncountable, like all of those real numbers?
Strangely enough, no.
Okay.
They're actually countable, just like our rational numbers.
So there must be other real numbers then that don't fit into that category.
Precisely. Those are what we call the transcendental numbers,
Okay.
which cannot be the root of any polynomial equation.
Okay.
Numbers like pi and e are perfect examples.
Wow. So we've got this hierarchy of infinities,
Yes.
countable rationals, countable algebraics, and then these uncountable transcendentals.
Exactly.
And it's all within this realm of real numbers.
Yeah.
It's really mind-blowing how much complexity there is to these concepts that seem so simple on the surface.
It speaks to this incredible depth in mathematics.
Definitely.
And it doesn't stop there.
Of course not.
The book even mentions Liouville's theorem, which helps us construct and prove the existence of these transcendental numbers.
Wow.
It gives us a glimpse into a whole other area of number theory.
So interesting. All of that just from exploring this fundamental nature of numbers. It's really remarkable how much depth there is to uncover.
Yeah.
But hold on to your hats, because the book doesn't just explore numbers in the abstract. It connects them to the world around us through geometry.
Yeah, it's like we can take these abstract concepts and actually visualize them in the real world.
Right, and it suddenly makes them so much more tangible and relatable.
Exactly. And the book does such a great job of this when it introduces this concept of the number plane as a way to represent complex numbers.
Okay.
Now, before you worry about getting lost in a sea of abstract algebra again,
Yeah.
remember those kind of strange imaginary numbers that we talked about earlier?
Right, like those equations with the square root of -1.
That's exactly right. So that's where complex numbers come into play.
Okay, back in school, I always wondered, how can a number be imaginary?
Right. It's a bit of a misnomer, calling them imaginary.
Oh.
It's not that they don't exist
Right.
or aren't relevant.
Right.
It's just a way to distinguish them from those real numbers that we use for everyday counting and calculations.
Okay.
Think of it this way. You can plot real numbers on that simple number line, right? 0 in the middle, positives to the right, negatives to the left.
Mm.
But complex numbers actually require 2 dimensions,
Okay.
a whole plane to visualize.
So instead of our familiar number line,
Right.
we have a number plane.
Exactly.
Okay, so how does that work?
So imagine a graph
Okay.
with 2 axes.
Okay.
The horizontal axis is our regular old number line,
Right.
our real numbers,
Right.
and then the vertical axis represents the imaginary component.
Got it.
So a complex number, let's say 3 plus 2i, would be a point on this plane.
Okay.
You go 3 steps to the right on the real axis, and then 2 steps up on the imaginary axis.
So it's like we're finding a location on a map,
Yes, exactly.
but instead of streets and avenues,
Right.
we're navigating these real and imaginary numbers.
Yeah. Exactly. And each complex number has its own unique position on this plane.
That's so cool. And what I find really fascinating is how this visualization then makes operations with complex numbers so much more intuitive.
Oh, absolutely.
The book mentions using parallelograms to add complex numbers, which sounds like incredibly clever.
It is very clever. It's actually remarkably elegant.
Okay.
You can think about each complex number as forming the side of a parallelogram,
Okay.
and then the diagonal of that parallelogram represents the sum of those 2 numbers.
Wow. So we're not just doing calculations in this abstract void anymore. We're actually like manipulating shapes.
Exactly.
It's bridging this gap between algebra and geometry.
And it makes it visual, right?
Yes. It makes it so much easier to grasp, I think, especially for visual learners like myself.
Absolutely. And it doesn't stop there. Multiplication of complex numbers also has a geometric meaning,
Oh,
and that translates to rotations on this number plane.
okay.
So the book introduces this thing called de Moivre's formula, which links complex numbers to trigonometry and rotations.
So we're talking about triangles and circles and all sorts of fun stuff.
Yes.
Okay.
It gets pretty deep, but the main takeaway is that multiplying by a complex number is essentially like rotating a point on that complex plane
Okay.
around the origin.
It's so cool how we can visualize these really complex mathematical concepts.
Right. And I think that's the beauty of it all.
Yeah.
Because you're right, these are complex ideas, but when you can visualize them, it just makes it so much more understandable and even, I think, beautiful in a way.
It really is.
Yeah.
And it makes you realize that math isn't just this like dry subject confined to textbooks, right?
Absolutely not.
It's all around us. It's in the shapes that we see.
Exactly.
It's in the way that things move and interact.
Right. And that's what this book, I think, does so well,
Yes.
is it helps us to see these connections
Definitely.
between these seemingly abstract mathematical ideas and the world around us.
It definitely does. And, it also leaves you with this sense of wonder and possibility.
For sure.
Because if we can uncover such depth and beauty just by exploring the world of numbers, imagine what other mysteries are out there waiting to be discovered.
Exactly. There's always more to learn. And that's the beauty of mathematics. There's always another layer to uncover, another connection to make. And I think that's an exciting thought.
It definitely is. So to our listeners, we encourage you to embrace the wonder of numbers, explore their hidden depths, and see where this mathematical journey takes you. Because, as we've seen, it's a journey filled with surprises and profound beauty.